This lab is about rotational dynamics. So we're going to study the rotational motion of this disk, and there is a string rounded around the axis and go over the pulley, and we have some hanging mass here. So because of the weight of the hanging mass, and the system will accelerate downward, and as a result, this disk will rotate faster and faster. And we have a motion detector here, and that's connected to Log Pro Vernier software. And there is a position time graph and the velocity time graph. So if we highlight the velocity time graph, we can get acceleration. This is the data I just collected. So position time graph and a velocity time graph. We want to find the acceleration. So let's highlight the velocity time graph and then use linear feet. And the slope of this line, 0.03119 meter per second square. That's the acceleration of this motion. So we use this method to collect the data. And here is the data table. We're going to try different hanging mass. So here M2 is the hanging mass. And the first trial, we do additional 50 gram on the hanging mass, and then 5 trial and calculate the average. And repeat this procedure for up to 200 gram on the hanger. And the acceleration from the computer, this will be the experimental acceleration. And theoretically, we can also predict the acceleration based on rotational dynamics. So here is a top view of the disk, and this is the string, and there is a tension in the string, and this tension is going to create a torque, and the torque is RT. R is the distance from the center to the string, and the radius of the small circle. And that's that torque. Because of that torque, according to Newton's second law, the disk is going to accelerate. This is alpha is the angular acceleration, and this is the torque, and the I is the moment of inertia. So the moment of inertia, depending on mass, depending on the mass distribution, and for uniform disk, it's going to be 1/2 mr squared. And in this lab, we have the big disk, we have the hanging mass. We use the little m1 to label the mass of the big disk, and the big R, that's the radius of the disk. And using this equation, we can find the moment of inertia. And the angular acceleration of the disk, alpha, is related to the linear acceleration of the hanging mass. And A over R just gives the angular acceleration. So these are 4 equations. And for the hanging mass, we can also apply Newton's second law. Weight point downward, tension point upward. And according to Newton's second law, the net force equal to mass time acceleration. So now we have 1, 2, 3, 4 equations. And you can solve acceleration. And here I'm going to show you how to solve the acceleration. And using the torque, we simplify to the torque. This is the first equation. And then using the hanging mass, you can solve the tension. And plug in this tension to this equation. We're left with one equation, the only unknown is the acceleration A, and we can solve acceleration A, and this is the final equation for that acceleration. So you plug in the little r, and the hanging mass m2g, and I is the moment of inertia, and plus little r squared, and this m2 is the hanging mass. So using this equation, you can find the theoretical acceleration in this table.